So my talk is going to be about the multi-point control unit. And in fact, I was very happy to hear the presentations today about the cloud and where things are headed and what needs to be done to make things happen. And I think that little box has been at the center of the problems that we have been experiencing, and it still is, but it's, in my opinion, it's slowly going away. That's why I use the term death. Now, in some discussions with colleagues here and elsewhere, they think that's kind of a strong term. MCUs are going to be staying around. They're not really dead. So what I decided to do is change the term to use, and I switched to use the term extinction. Because I think that's more representative of what we are actually experiencing. And we're actually living it, so it's very difficult, in my opinion, to be very clear about what is happening around us, but I think the signs are very clear, okay? The predators are out there, the environment is changing, the MCU will not have enough food to survive. So I looked for fossils of the MCU, see where it lived, where it came to be. Now, I did a Google search on multi-point video conferencing. The earliest reference I could find is a paper in '87 in England. I couldn't find the actual paper, unfortunately. Maybe I was too lazy to go find the printed one. I couldn't find it online, that is. Now, what I could find online is the earliest paper that was in the IEEE Explorer. For those who are not in research and development, that's IEEE is a large organization and publisher of technical papers in our field. So the earliest one I could find was from '92, to my surprise. I sort of assumed there must have been work before that. And in fact, it was actually in Europe, in a European project, for that matter, talking about, ISO 261, sorry. Out of habit, I typed 264. No, it was 261, 64 kilobits, and so on. But it was multi-point. And it was referenced actually a service in England that was doing conferencing, but it was point-to-point and analog, okay? Now, if you look at the commercial space, clearly PictureTel stands out. In fact, it's maybe the earliest or maybe the earliest company to have an IPO before having a product. So it was done in '84, first program in '85. And the M8000 bridge, I guess, is the earliest product that I could find, at least again online, that had the multi-point capability. 8 conferences, 16 users, $75,000 base price, and actually later on it was cascadable to be able to support 240 bridges. So just as a comparison, ISO 323, the standard which is now used for multi-point, was done, first version, November '96, okay? So that's that's how things got started. So if we look at the MCU types, first of all, let me show you how I'm going to be depicting the streams and associated videos. So the horizontal bars are bit streams carrying video. The image sort of shows what that bit stream contains, okay, the video image. And by the way, I don't know if you recognize those pictures. Those people in the United States probably do. They're Republican senators. I took them from an article in the New York Times, on the debate about the budget program. Okay, so the simplest, the simplest MCU is obviously switching MCU. You have 4 incoming streams, A, B, C, D. The MCU decides which one to send to the other participant. In this case, is B. Okay. Then you have the mixing MCU. In the early days, when you had QSIF and SIF, you might encode QSIF. Very small size, you send it to the MCU, and the MCU would combine the ABCD pictures, which were small, into one big picture, okay? And of course, the corresponding bit rate would increase, okay? But that doesn't require any processing from the MCU, except from some, modifying a few headers. Typically, there's no signal processing involved. And of course, the more sophisticated one is the transcoding MCU, where you have incoming streams that are decoded at the MCU. Then there is composition to recreate the new frame, encoding and transmission of that resultant image. So in this configuration, you have a very sophisticated device that can do very complicated signal processing. That introduces, first of all, high delay in the order of 200 milliseconds. Okay, you have transcoding loss. meaning quality loss because you have this cascaded processing of the video signal. And of course, it's complex, it's very costly. Now, you might be able to live with transcoding loss. You might be able to live with complexity and cost, just throw more money at the problem. You cannot live with delay. Delay is something that is non-negotiable. The way we interact cannot take delay. So for multipoint, the MCU has this fundamental architectural limit of introducing delay, which is beyond the limits of what we can tolerate. Where for end-to-end, you would need something in the order of 180 milliseconds, ideally. Okay? So that has been a key problem because it doesn't allow the technology. First of all, it doesn't allow the technology to be cheap, but it doesn't allow it to be transparent. Okay? And unless the technology is sophisticated enough to provide extremely high quality and be transparent, it's not going to be used. Unless there is very compelling reason to be used. I need to have a conference call. Okay? So that has been a key, I think, impediment. Now, the canon of systems in the RTP world, in the ITF world, okay, recognizes the transcoding MCU. So in the RFC 5117, which was actually done in 2008, there is a topology which is associated with this transcoding MCU, the topo RTCP terminating MCU. Okay, so that's good. Now, the key disruptor, not the only one, the key disruptor for this MCU world has been scalable video coding. Now, those that know video, you know that the first thing we did when we started in 2005 is get involved in the development of the SVC standard in H.264. And we're actually the only video conferencing company doing that. The standard was already half started, okay? But we believe that it was a key for making things, for changing essentially the architecture of the MCU, and that's why we started from there. Now, allow me to digress very quickly on the structure of SVC because I think it's important to make a few points. So very quickly review some aspects of how SVC works for the benefits of those that may not be familiar with it. So this slide shows a sequence of video pictures, okay? Now, I'm not going to be showing actual images just to keep the pictures lightweight. So in traditional coding, you predict one picture by using the immediately previous one as a reference. And you create a chain. That is very good for compression efficiency. You transmit it, and everybody's happy. Now, if something goes wrong with the transmission, if one of those blocks goes away, you have a problem, and you have broken pictures, etc. That's very well understood, and that has been a key problem in robust video transmission for many, many years. So with scalable coding, the idea is that you'll create a set of layers. So in this instance, I'm going to select one every 4 pictures, and what I'm going to do, I'm going to give them a name. This is my layer 0. And what I'm going to do is code them as I would that single layer picture that we used to do in the past. And then what I'm going to do is I'm going to be adding pictures, those that I left out. But now I'm not going to be coding them in a single chain, but I'm going to be using the previous layer as a reference. So 1 uses 0 as a reference, and I can add 2 that uses either 0 or 1 as a reference. Okay? So now I have a much better picture. Why? Because if you lose any of the 1 or 2 blocks, you don't get serious damage because it would not propagate to future pictures. Okay? You would still get problems if you lose one of the 0 pictures. Okay? But the fact of the matter is that because now these pictures are very far apart, previously they were right after each other. Now, because they're very far apart, there is time to react if you lose any one of those pictures. So you can actually retransmit. If you lose one, you can retransmit it before you need it to decode the following one. Okay? So with this design, you get both robustness because of losses, but also get the ability to react, to actively respond to a packet loss. That was impossible with traditional single-layer coding. Okay? Now, scalability can work also in resolution. So in this instance, you can use a small picture. You can upsample to predict the high-resolution picture. Okay? So you can have a combination now of the two. Okay? And I know this looks complicated to those not familiar with the design. So to keep things simple, I think we get the message that with scalable coding, you have multiple components in the bitstream that allow you to represent the content in multiple levels of fidelity, either temporally or spatially, even in terms of SNR. And that's depicted below with this two-color stream. The single layer is traditional coding, one bitstream alone and one resolution. Okay, so for scalable video coding alone, let's forget about MCUs, etc. You get approximately 20% more bits than single layer coding. And a lot of people, when we went to do SVC and were advocating for the use of SVC in video conferencing, they were saying, but you're spending more bits than single layer. It's more expensive. You shouldn't do it. Okay? But the fact of the matter is that you get superb error resilience. You can tolerate packet loss rates of 20% or more, which are very common in day-to-day communication. Something is inconceivable with single-layer coding. Okay, and the parallel I use for this is four-wheel drive. That if you want to drive on an icy road, right, you prefer the reliability of four-wheel drive. Now it's more expensive; it consumes more gasoline, right? But you'd rather pay a small premium in advance in terms of more expensive car and more fuel consumption rather than pay for the car itself when it's going to be destroyed afterwards. So what we did with scalable video coding, and I think that was the more important contribution, is what we call the video router as a product. Now, what does it do? It gets scalable coded video from multiple participants, A, B, and C, you see on the left side. And what it does, it selects what it should forward to the receiver, okay, without any processing whatsoever, right? So no signal processing whatsoever. So in this particular instance, it selected some base layers for some pictures, and for one, the B, it selected the full resolution signal, okay? That is just it's a packet filtering, so to speak, decision. It doesn't have to do any processing. Now, what do we gain? We get the error resilience and from SVC. Okay, we get the rate matching because I can adapt. The scalable nature of the signal allows me to adapt. You get the personalized layout because the composition does not happen at the server, and as we'll see, it's actually going to happen at the client. You get low delay, and that's a huge, huge benefit. You get less than 20 milliseconds delay to cross that simple device. That's huge. You get error localization because of the scheme with SVC, and of course you get low complexity. Something that I left out is cascading, and that's very important for the cloud applications that Alago was talking about. You cannot cascade MCUs. If you do that, you have 180, or let's assume it's even 100. Okay, you have a very fast whatever. You cannot cascade MCUs because the cumulative delay will just throw you completely out of the interactive region. So if you want to deploy something globally where you have multiple servers located, right, this just cannot do it with a traditional MCU. Okay, this shows an example just to get a perception of the difference in magnitude that we are talking about of how many rack units you would need with traditional transcoding MCUs and something that works like the video router. So 6U for a video router and about 114 for a transcoding system. So it's huge. Now there's another very important component, however, and that is what happens on the client side. Now I think that's extremely important as well. Now the MCU will transmit those. The video router, will transmit the different components to the endpoint. Now, what does the endpoint do? First of all, it has to have the capability to receive multiple streams. It's not going to receive a single video. It will get multiple video signals, okay? Because the composition will happen where? At the endpoint itself, okay? So you have a multi-stream capability and composition at the endpoint. And in fact, that's exactly how your web browser works, right? The web browser obtains content from the server, and it does its own rendering and composition. And that's key. Why? Because if it was the server that did the rendering, imagine the level of scalability we could have achieved for web servers. It will be abysmally low, right? So it's key that the web server does nothing but fetch content because it allows it from a single cheap device to serve thousands of requests, right, per second. Whereas if it actually had to pre-render the images, okay, it would be a very expensive service. So I think this is a key feature of this design, and something which is absolutely necessary if you ever going to see ubiquitous video. I mean, the scale of millions and millions of users. After this was done, people started looking at a very similar technique, which is called simulcasting. Now, with simulcasting, instead of coding multiple layers of a signal, you just code it twice. So you code it in high resolution and low resolution, and you can transmit both of those streams. And so some companies do that, and you can have sort of that new type of server in its Simulcast Edition, where you send both high and low resolutions to the server, okay? And then the server will decide which one to send to the recipient. Now, this is very funny because, again, we had arguments that our scalable video coding wasted bits compared to single layer coding. And it's very funny, after 3-4 years, to see people willing to spend even more bits going to simulcasting. Okay, why? Because they want to reap the same benefits. But they're spending more bits than SVC. Okay, simulcasting will, if you have a properly designed SVC encoder, by definition, because simulcast is in the design space of the encoder, if it does worse than simulcasting, it could do simulcasting. Okay, so it's always going to be worse. So how do we call this new device? Well, there wasn't a name for this. The RTP protocol and the RTP topologies draft did not have a name for this new device, whether it uses SVC or simulcast. Okay, and there is a new draft actually from Estelund and Wenger. Stefan Wenger is actually with Vidyo, and they call this the media projecting middle box. Now, I don't know about you, but I don't want to be going around and giving talks like this one and speaking about the media projecting middle box. Okay, I think that's a bad idea. So my proposal, and I made that proposal to Stefan as well, is to use something like selective forwarding unit. In other words, a device that basically just selectively forwards content. Okay. Now, so the beauty of this is that it does require SVC. And again, a lot of people associate video with SVC. Obviously, we started with SVC. We spent a lot of time there. Right? But the point is not scalable video coding as it's implemented in H.264. Okay? Any scalability works in this scheme. So 264 has scalability, of course. Both SVC and by the way, AVC has temporal scalability. VP8 has temporal scalability. H.265, HEVC, has temporal scalability. And in fact, on all these three cases, the RTP payload formats support that. Okay? And of course, HEVC is coming in July 2014. SHVC, the scalable version of HEVC. Okay, and VP9, I'm sure you all saw the announcement, will have scalable features. So to me, the important part is that scalability is a key component for packet video. You absolutely need it, and I think from now on, all codecs will have scalability because that's a way to do it going forward and living on the internet, okay? And then you have the SFU, the selective forwarding unit, to have the low complexity server. Now, who is using that? Actually, a lot of people: Cisco, Google, Polycom, Microsoft, Vidyo. These are companies that I know for sure that are in production or in development. There may be others. This is not supposed to be exhaustive. And there are also other companies that are using SVC alone. But again, if you use SVC alone, you get some of the benefits, like error resilience, but not all of them. Okay. Now, to me, it's very interesting the WebRTC angle. We spoke, yesterday, I guess, about WebRTC. The point to make here is there are two points to make. First of all, that for WebRTC to take off and succeed, it has to be able to rely on video services that can be easily developed and deployed. Okay, that means they have to be compatible with other types of network services that we use, like databases and web servers. So you have to be able to throw a 1U device somewhere, and boom, you got a service running. And I think the only way to do that in an economically viable way that can scale is with SFU. Okay. And the second point I wanted to make about WebRTC is that just because we can actually encapsulate the complexity in a tag, we should not have the false sense that what happens below our layer of the API is simple. It's actually very complicated. The interactions that exist between the WebRTC client and the server to get very high quality, I should say the video client and the video server to get very high quality video are very sophisticated. Okay, so we should not think it's just a matter of coding the video and just sending on the other side. Okay, so in a nutshell, again, scalability is key for error resilience and low delay, which I think both are essential for a transparent experience when using video. The SFU design, I think, can make video like any other network-based application, which, again, for cloud and WebRTC, I think it's just the way to go. There's no other way. And I think thinking about ubiquity and scalability in terms of the millions of users, already I think we are seeing transition of a lot of companies in that direction. So I think that's good, and that means we now have a good foundation to build next generation of applications. Okay, as in nature, in all aspects of nature, here as well, we see evolution at play. Okay, things change, things adapt, but hopefully, new things come to our lives. Okay, thank you very much.